There's a misconception in many textbooks as well as online that the atom is empty. The atom is not empty, but to set it up, let's give an analogy first. So, analogy. And I want to talk about the analogy of I'm going to think about golfing. So when I think about golfing, I imagine that I have some type of course where this here is called the tee-off area. And with the tee-off area, we could imagine here that we have some golfer that sort of is gonna golf here. And he's gonna hit this golf ball along the fairway here. Now, when I imagine a fairway for a golf course, what I think about here is that that golf course is empty. So what do I mean by empty? If you think about the longest golf hole, so this would be the golf hole where you're trying to put the ball into this hole, the distance from here to there for the longest hole here, right? So this is the longest hole, and this turns out to be about 1,600 feet, which is about 1/3 of a mile. So if you were to walk from the golf tee area to the golf hole, what we say here is that this is, if there's nothing there, we then say that it's empty. Nothing is between the golf tee area and the golf hole. Now, to apply this analogy to the atom, so now if I go to the atom, the atom is said to be empty. Now, what does that mean? So you could imagine that instead of the golf hole, I have my nucleus. And if I look at the electron, especially if I think about hydrogen, the first electron is right here. So when I start to look at between the electron and the nucleus, it's common for people to say that this is empty space in between. So the analogy is that because there's no physical thing in between the electron and the nucleus, they say that the atom is empty, very similar to a golfing hole where the fairway, there's nothing there, but it's empty. But it turns out that that's far from the truth. The space between the electron and nucleus is filled with very intense electric and magnetic force fields. These force fields are so strong that even with today's technology, we can't reproduce them. If somehow you were small enough to enter the atom and you tried to go in between the electron and the proton, you would be stopped instantly because these force fields are so strong. It is these force fields that give solidity to matter. even though supposedly these atoms are empty. And this example of how strong these internal fields are is historically given by Rutherford's gold foil experiment. So if you go and you look at history, this is known as Rutherford's gold foil experiment. And it was this experiment that discovered the atomic nucleus. The way Rutherford discovered the nucleus is that he was shooting these things called alpha particles to a very thin piece of gold foil. So you have a gun, and this gun here is shooting out these things called alpha particles. These alpha particles are helium nuclei. In other words, if you were to look at the nuclei of helium, it has 2 protons, 2 neutrons. So these guys are positively charged. And what Rutherford did here is that he shot them at a piece of gold foil here. So you could imagine that I have this piece of gold foil. Now, gold foil is super thin. So this is the gold foil, and it's very thin and fragile, and a lot of times people kind of think of this as tissue paper. But it turns out that the gold foil is thinner than tissue paper, so it's very, very, very delicate. And because it's very delicate, what Rutherford expected here is that these very high energy alpha particles would blast holes through the gold foil. But this did not happen. The electrons did not blast holes through the gold foil all the time. So what you found here is that some of the time the alpha particles bounced back. And this shocked Rutherford. So this was a big shock. Because if the gold foil is thinner than tissue paper, and if I'm shooting these very intense alpha particles towards this gold foil, this should not happen. And one of the most famous quotes in science was given by Rutherford that said this here, that it was almost as incredible as if you fired a 15-inch shell and the 15-inch shell is the equivalent of the alpha particle, at a piece of tissue paper, and the tissue paper was the gold foil, so it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This was Rutherford's quote about alpha particles being having that being the case here. So what ended up happening here is that he concluded, so then from this here, Rutherford concluded there was a nuclei to atoms. So what ended up happening here is that you could imagine that you were shooting these alphas at the gold foil, but what these alphas were actually interacting with was the nucleus. So there was tons of protons in the nucleus here, which means that in between here there is an intense force field. There's an intense force field because as these alpha particles got close, what ended up happening is that they got deflected back. So that means here that the atom is not empty. So this implies here that the atom is not empty. And it was the deflection of these alpha particles that showed that that was not the case. So in between here, you have this intense force field. And this is quite different than the golfing hole, between the golf tee area and the hole.